So I did a PhD in electrical engineering at Columbia, and in that I was developing custom camera chips that look at not the color of light, but the temporal properties of it. So how it changes over time, and these timescales are really short, on the order of nanoseconds. So, and the reason this is interesting is because a lot of biological molecules have properties that can be measured optically through these very short timescale measurements. And so it's a technique called fluorescence lifetime imaging, and it's all based on time of flight measurements. So I had a PhD basically designing custom time of flight chips. And in that, I kind of learned everything from the device layer. So how the PN junctions and diodes that detect the light, all the way up to the software layer work. So kind of everything in between, designing the circuits, designing the boards, writing some low-level firmware, writing software. So it gave me this really broad experience to start out with, and kind of a good understanding of whole systems. From there, I had a short time at Intel working in their research labs on some biosensing platforms. Then went on to a startup called Quanergy, where I was developing a LiDAR sensor. So going back to my roots, what I did my PhD on, and doing time of flight measurement. We send these pulses of laser light out and see how long it takes to come back. So we know the speed of light.
That's why you're measuring them. You measure them for that? Because I was making notes. By the way, if I look down, it's because I'm making notes. But I was like, why would anybody care about why light changes on a nanosecond level?
In LiDAR, that's kind of on a microsecond level. So it's different time scales, but same principle. So you're pulsing laser light and looking at microsecond time scales. And so I worked there for a few years, developed some detector technology, built up a team, kind of grew that kind of detection team up quite a bit. And then I was approached by the team at Kernal and Brian Johnson, who had this idea of measuring the brain using time of flight on the nanosecond timescale again. So going back to these shorter timescales that I had done my PhD on. And so the concept is you put in a pulse of laser light and you look at how that light changes over time for this short few nanoseconds. And that tells you something about the properties of the tissue inside the head. And you can, by detecting changes in those properties, tell what parts of the brain are active in a certain time. And this is kind of a well-understood phenomenon. It's been around for many decades, but it had previously existed as kind of racks of equipment in, research laboratory, and never as a integrated device. And so sounded like a challenging problem, and I had the right skills. I had the experience building the teams, and kind of decided to join and start helping build up that technology and figure out what exactly to build and how to build it, and what the right technology stack was, and everything along the way to get to what is Kernal Flow today. So it took us about 4 years, a little over 4 years to get here, but we've got something working, and we're kind of putting the finishing touches on the production release for later this year.
What can I do with it?
I'll tell you what it does fundamentally, and then we can talk about what that could tell you kind of from an applications perspective. So fundamentals, are you familiar with a pulse oximeter? So you may have like a smartwatch that has like an SpO2 sensor in it, or if you've gone to the doctor or hospital, they clip on your finger. That's a pulse oximeter. It's measuring the oxygen in your blood. And so fundamentally what we do with Kernal Flow is we generate a map of blood oxygenation across the entire brain. So we're seeing small differences in oxygen in your blood throughout the brain. And what that tells you is what parts of the brain are active. So as the brain does work, or parts of the brain does work, it needs, or those parts need some oxygen in order to do the metabolism, to fire the neurons to produce the function. So Kernal Flow measures that change in oxygenation, and this is what's called a hemodynamic measurement. So we're looking at changes in hemoglobin oxygenation. So the hemoglobin is the thing that carries oxygen around in your bloodstream, and we're measuring how much of it has oxygen versus how much of it doesn't. And we use a technique called near infrared spectroscopy. So we use 2 wavelengths of light, which is a spectroscopy component, and it allows us to differentiate the oxygenated versus deoxygenated. So high level, we're measuring blood oxygenation as a map of your whole brain. And what you can do with that is you can start to ask questions like, what is my brain doing when I'm just sitting, kind of daydreaming, staring off into nothing? And this is what's called, resting state. This is what the brain looks like when nothing is going on. And
resting brain face.
Yeah, resting brain face. And so it's just like one very simple example. Another is, I think you probably saw some of the work we've done, like playing video games. Right? So like, what is happening in the brain when a person is playing video games? And we have this hypothesis that, we would see actually almost the entire brain light up. Like, you're using so much of your brain playing a video game. You're using your motor cortex to control a mouse or keyboard. You're using your prefrontal cortex to plan out activities and how you're going to move or what your next point in the game is. Your visual cortex is lit up as it processes all of this, visual information coming in. The parts of your brain handling auditory or processing sounds, like trying to, a lot of games use spatial audio type tricks to give you, signs and cues for what's happening in the world you're in. So much of your brain is being activated by video games. And we actually saw this in some of the measurements we took, is that, when you play video games, tons of stuff is happening. It's not actually bad for your brain. You're actually working out the entire brain when you play these games. So, and those are just a couple of examples. I mean, we could probably talk all day, like, could you measure the brain while doing X? And the answer is probably yes. And one of the things that Kernal Flow enables is asking questions in a new way, because it's now a portable device and you can kind of use it in more naturalistic environments. And we could talk a little bit, if you're interested, in kind of what the legacy devices, what the whole history of functional brain measurement was built on, and how those don't really quite provide the same type of experience.